Excellent. Well, thank you very much for coming. I hope you enjoyed the conference so far. I'm going to talk about how an emerging architectural pattern with a horrible buzzword called serverless is impacting the way we design software. Now, kind of in this community, we are very, very, very precious and precise about the language we use. So I'm going to have to introduce a few words, how I use them in this talk first, so we don't misunderstand each other. And I think kind of if we look at the whole idea of domain-driven design, most of what people actually do is not design. Most of what we tend to do when we talk about domain-driven design is mostly, at least in my terminology, my view, about modeling. And domain-driven modeling wouldn't sell nearly as well as domain-driven design, so Eric decided to kind of, use the branding better. Now, I do mean an impact on design, not on modeling here, because I think modeling is much more bound to a particular business, a particular market opportunity, a particular way we want to capture the world. So I want to talk about first a bit difference between modeling and design. So in the context of this talk, modeling is kind of figuring out how we are going to build a theory about the world we want to represent. Peter Nauer in the 80s published a very influential paper on how programming is actually theory building. We're building a theory about the world around us, how it works, we're trying to kind of capture that. And in the 80s, kind of basically everything was called programming anyway. But then we started splitting this thing out. So this building the theory about the world, the joy of discovering that there is such a thing as a shipping container and that, for some reason it has legs or whatever, that's modeling. And then how do we capture that and how do we translate that more into software? That's what I call design. So although these two things, of course, are not exclusive and there's a lot of overlap and we do modeling and we do design at the same time and things like that, it's important to kind of make a distinction. So kind of modeling is building the theory about the world. Design is where we take that theory and we say, look, this is actually going to be a service. This is going to be a repository. These are going to be, classes. Now, we can talk about deciding whether something is an entity or a value object is modeling or design up until we go blow in the face. I don't really care about that. But there's kind of, somewhere on this line, we start with building a theory. Somewhere on that line, we end with software. And in terms of what serverless influences, the serverless influences the second part a lot more than the first one. That's important. Now, there is a third part in this that typical design tends to ignore. And the third part of this that's really interesting is to think about deployment. Now, in the context of this talk, when I talk about deployment, I mean figuring out, well, this is going to talk to a database, and this repository is going to sit on, a scaled cluster of services. This repository is going to talk to a queue and things like that. So traditional design tends to kind of imply deployment. Once we figure out the design, we can say we want to deploy this on a cluster of Windows servers, or Windows is never going to touch this because we want it to work. Now, one other kind of interesting thing about this is most of what we talk about when we do modeling ignores deployment as well. And I'll come back to this later. Now, the last term that I just want to introduce before boring everybody to death with terminology is what do we mean by server? Because when we talk about serverless, it's a question of what is server. And that's not as easy to define as people would think, because there's 1 million blog posts online how serverless still has servers in, so it's not really serverless, and things like that. So in the context of this talk, when I talk about a server, and we look at the deployment, there's usually two types of servers people think about. One type of servers are physical machines. They are boxes, they have lights, they blink, they hum, you pull out electricity, they disappear and things like that. You pull in electricity, they kind of restart. The other type of what's called a server is a program that operates a socket. It's a web server, it's a message server, it's a system where it waits for some network request to come in. Now, the context of serverless is very, very confusing because if you do serverless, there's a lot more of one type of servers and a lot less of another type of servers. So when we talk about serverless, generally that means your app is going to run on many, many more things like this, but you don't care about this stuff anymore. The whole idea of serverless is that the provider of the platform terminates the socket, and the provider of the platform owns the socket. Your app no longer starts a web server or a message server or something like that. Somebody else does it for you. So serverless is serverless the same way wireless is wireless. We all know that somewhere in this room there is a router, probably more than one, and there is a wire, an Ethernet wire stuck into that router. But we can browse the internet without caring about that wire. Somebody else manages that. So that's kind of serverless. And all these complaints that, yes, there are servers in serverless. Well, of course, there's wires in wireless and, things like that. So now, we're done with the terminology. I'm not going to bore you with the terminology anymore. But what's kind of interesting here is this buzzword is horribly stuck with us now. For some insane reason, marketing was good about that. And now it's everywhere. So it's a lot technically better to think about not serverless, but socketless, where most of these platforms have a similar programming model. The programming model is basically you implement a handler for a request. This is how you do AWS Lambda in Java. There's kind of handlers for different types of languages. They're very, very similar. So you have a request handler, and pretty much you do something interesting when a request comes in. Now, how a request comes in is not up to your code. It's how you configure and how you deploy to the platform. And deployment becomes really, really important. The traditional modeling design spectrum kind of implies deployment after design, or once we have a design, we can figure out the deployment. In the serverless world, the deployment becomes really, really critical. We have to think about the deployment when we do modeling, and I'll talk about this thing later, because kind of this do interesting stuff later becomes really, really critical how we deploy stuff. Now, an event, in this case, in 2014, was actually you pushing something onto a queue. And you were able to do that only if you worked for Amazon. In 2015, you started being able to do that even if you don't work for Amazon. In 2016, we started being able to receive events from HTTPS, we started being able to receive events from message queues, and 2019 you can receive an event into this for pretty much anything that happens on the cloud. A user registering, a user deregistering, a payment coming in, a service going up, a service going down, technical stuff like metric thresholds being exceeded, business stuff like your sales dropping, incoming emails, database records being written, kind of pretty much anything that happens on cloud providers, you can now act on in this way. Which opens up some really, really interesting possibilities. So, for example, when we look at the different types of clouds and different types of providers, pretty much all of them have started adopting this as a universal integration strategy. And generally, almost all cloud providers started copying Amazon now. Currently, this is data from about a year and 3 months ago. I don't have any more updated data, but about a year ago, Amazon held about 70% of the market here, but Google had their own cloud functions, Azure had functions, Huawei had functions, IBM had functions. Meanwhile, IBM decided to open source their functions and donate to the Apache Foundation, which pretty much means they've given up on it. When something goes to the Apache Foundation, they failed as a business and decided to kind of just offload it somewhere. And you know, Twilio has functions and who knows what else. And what's interesting about this is not only is it becoming an execution mechanism where you can design the apps, it's also becoming an integration mechanism. Cloud providers and other providers are allowing people to customize their platform using this stuff. What's really interesting about this is because they own the socket. Once they own the socket, they can do interesting things about this as scaling, as securing it, as retrying things, as monitoring it, and things like that. And they can hold everything within a boundary that they like to hold. With typical integration patterns that have been online for the last 10 years, like webhooks, what happens is you run a bit of code somewhere. The platform provider runs a bit of code somewhere, like a payment provider. The payment provider sends you a webhook. Then first you need to validate, did the webhook come from the payment provider? Or is somebody else forging this? And then you have to say, okay, is this webhook consistent with what I expect? And then you have to do something with that. And then the payment provider has their own policy saying, you have to give us a confirmation in less than 3 seconds, otherwise we're trying it again. So you're crazily trying to kind of figure out what you can do within these 3 seconds, and you don't know how much the message is going to travel back. And then if it fails, they don't know if they are safe to retry or not, and you need to build a complex system here. Once the provider owns the socket, they can deal with all of that. And that's what's really, really interesting. So apart from just an execution platform, all of these providers have started opening hooks into their products. For example, the picture behind me is a configuration screen for Cognito. Cognito is Amazon's username and password management system for users. And you can just take that and build an app on top of it. So it will support secure authentication, it will support integration with various integration mechanisms and you know, a bunch of other things. But you can also customize it by telling it to run this serverless function when something happens interesting. For example, you can see pre-authentication over there is configured. The product I'm building is used a lot at schools. And every now and then we have a clever teacher who registers for a personal account and then decides to share a password with everybody at the school. Now, okay, you know, we don't want to support horrible abuse, but we want to support teachers sharing with, you know, 5 or 6 children or sharing at the class. That's okay. So we tolerate that. So rather than building my own user management system, just because I have that tiny business requirement that's different from the standard, what I can do is I can say, look, I'm going to use this, you know, generic thing almost in the domain-driven design sense, but I will add this teeny tiny bit of functionality that's specific for me. And instead of creating a webhook and making this horribly complicated, Amazon is going to run it for me. Amazon knows that it's my function. Amazon knows that it's in my security context. Amazon knows when to retry. A ton of stuff becomes simpler. So this function basically says if we had more than 20 logins in the last 24 hours from the same account, kind of reset the password and send them an email. That's my specific case. Everything else is generic. So what that kind of allows us to do is allows us to maybe not think about serverless but webhookless. It's a different integration pattern where the provider will run the code and you pay for utilization. You pay a tiny bit not for running a service on your end, but maybe you know how much they run that function. And what's also kind of really, really important here is the provider owns security, availability, recovery, and all this other stuff that's kind of embedded in it. Simon Wardley joked about serverless, and he said that kind of if you've not done DevOps yet, just don't bother at all. Skip the whole generation by going serverless because you get DevOps included in the price. The provider owns that problem. It's not 100% correct, but there is, you know, some truth in it. Now, what is an interesting trend now is we are seeing kind of second-level providers, not bottom-level cloud providers like Google, Amazon, and Microsoft. We're seeing second-level providers of applications implementing this as an idea. For example, Atlassian started a service called Forge. It's still in beta, which allows you to kind of give them a bit of code to run to customize their products. So, you know, Jira is perfect for you. But you want to make it more perfecter, if that's a word. You know, you just do the tiny, tiny bit that's really different. Add it there, Atlassian will run it. You don't have to kind of worry too much about that. They will worry about all of this stuff. Twilio does something similar with Twilio functions. Netlify does something similar with Netlify functions. In fact, they're actually reselling Lambda. They're just adding a bit on top of the price, so everybody's happy. But this is a integration pattern that's going to be more and more interesting. And the reason why this is going to be more and more interesting is kind of we can start building only the bit of stuff we need. I don't have to build a user management platform just because I have some, 5% different functionality from the existing one. I can kind of pretty much get all the generic stuff from Amazon or Google or whatever. I can integrate with different providers for supporting and provide these kind of small bits and pieces that we need, and I can really focus on what's core for my stuff. So domain-driven design really talks a lot about focusing on the core, but there's core is a small part of the system. There's a ton of other shit we need to build. Where serverless is really where domain-driven design becomes show me the money. That's where kind of really good design starts becoming important. So what's kind of interesting here is the pricing model for serverless is where things become really, really interesting. Technically, it's just a container management system that works fast. But Amazon, Google, and Microsoft have grown so big in their services that they can bet that enough people will use something like this for them to keep a lot of reserved capacity. Tim Wagner, who headed the Amazon Lambda project in 2016, defined the pricing model as kind of never pay for idle, only pay for what you use. And they're going to kind of deal with this to make sure it's available. So for example, I have a small test website that allows me to run kind of performance tests on this. It is, let's see if I'm online. So I can, at the moment, I've deployed a bunch of things there. I'm not paying for anything because nobody's using it. Now, Amazon, Google, and Microsoft bet on enough people using this stuff, so if I kind of get 1,000 users to use it at a batch of 10 now, they're going to kind of start spinning up new instances. Now they're starting new containers like crazy, serving my requests and charging me for what's being served. And at this point, I've kind of gotten between 24 and 43 milliseconds and 24 to 77 milliseconds, 95% usage. It spin up 11 instances to handle this stuff. By this time, it probably killed these instances and charged me for what I used. And that's the really, really interesting thing about this, because I don't have to plan how much capacity I need. One of the biggest architectural constraints over the last 20 years is figure out how much is the right amount of capacity for this, reserving the capacity for that, paying for the reserved capacity. Where with this stuff now, we are not really paying for reserved capacity. Amazon is paying for reserved capacity, or Google or Microsoft. We are paying for when this thing is used. And there's a couple of the pricing model is almost the same for all the providers at the moment. They charge you a certain amount of money per request. And at Amazon, it works out to about $0.2 for 1 million requests. It's actually prorated per request. So what I executed was like 1,000. So they're going to charge me 2 cents for what I just did. They charge for time spent in the processor based on the maximum amount of memory. Now, these two things are really important for what comes later, so you don't need to worry about individual prices, but kind of more or less everybody charges the same. Google is slightly more expensive than Amazon and Microsoft, but you get a larger free tier per month. And kind of the pricing is relatively comparable. But what's priced is the number of requests and the time spent in the processor times memory. Utilization. What that means is that we remove an architectural constraint that's been with us for the last 60 years. That is reserving capacity when we're planning. From immortal mainframes to applications deployed to a Google App Engine or Heroku, we were paying for reserved capacity. And what that leads in is, in deployment, not in design, in deployment, we are bundling things together. We have 2 expensive production machines, and we have 500 different services we designed, but we deploy them on these 2 machines because we have 2 expensive production machines that are properly secured. Or we've rented 10 virtual machine instances from Heroku or Google App Engine. We build lots of these different services. We design them to be decoupled. We designed them to be isolated, but we deployed them together. For example, with the product I'm building, we do a lot of file conversions. We have about 20 different file converters. One file converter is converting from the source format to PDF. It's used all the time, like everybody's using it all the time. Probably this very moment about 10, 15 instances are processing that. Then we have Markdown that I built for myself. I use it 3 times a month. Probably nobody else uses it. And we have everything else in between. Now, if we wanted to kind of do this properly, and we design these things as isolated, we need to kind of keep about, 200, 300 instances ready for failovers, for kind of plant capacity. We'd have to isolate every one of them and plan. And that would cost a lot more than the actual capacity we need, because I can serve everything with about, 10, 15 instances. So what we did when we were on Heroku, where you pay for instances, you pay for reserved capacities, we designed them to be isolated, but we coupled them together in deployment. And then the SVG exporter, we had a bug, and it did not clean up temp space correctly. When you fill up the temp space on Linux, it starts misbehaving crazily. So all these 10 instances we had, basically, like dominoes, fell because of that bug. Now, the point I'm trying to make is this. We design things by implying deployment, and we design things to be nice and decoupled and brilliant, but then we deploy them to be coupled because we're paying for reserved capacity. And then we couple them without intending to do that. And this is kind of the problem, because so far, deployment architecture was rewarding that type of work. Now, with Amazon and with Google and with Azure Functions, what you pay for is the number of requests. So the number of requests, if you have 50,000 people asking for PDFs, 5,000 people asking for images, and 1 person asking for Markdown, you pay exactly the same, whether it's deployed completely isolated, every single thing into its own application, or as a single application. Even better, if they have different memory constraints. If the PDF one that's using Ghost script is a memory hog and needs a lot of memory, the SVG one is working on text files, by breaking them apart, you pay less. By deploying them individually, you pay less because the SVG can work with less memory. So, because we're paying for utilization, not capacity, not instances, not environments and things like that, lots of interesting things open up. And one of the really interesting things that opens up is basically serverless starts financially rewarding good design. Decoupling things, what we've been preaching for the last 30 years, designing things to be nicely isolated, having nice boundaries and things like that, kind of isn't really rewarded when you bundle everything together. The reward for that is, when the business changes 6 years in the future, we'll be able to kind of easily change this stuff. That's why there's so much technical debt around the world, because business people don't really care about that. Serverless immediately rewards good design. And that's why I'm so obsessed about this. So here's some hard data. For the product I'm building in 2016, we started moving from Heroku, that's reserved instances, to Lambda. In 2017, we kind of finished the migration. During that time, the number of the users increased about 50%. Our hosting costs actually dropped about 50%, which means that we had about 66% saving there on our costs. And not only that, we were much, much, much faster deploying the stuff we wanted to deploy. In a sense of taking business functionality to the users, because we could focus on individual things we want to do. We could focus on kind of the core, not the generic or the supporting part. IDC did some research last year, and they claimed that based on the companies they surveyed, the average company saves about 60% on operating costs. That's kind of consistent with what we did. But also, they're about 89% faster taking business features to the clients. And I think this is the money shot. This is the give me the money version of show me the money version of serverless, because this is what's going to put pressure on people to adopt this kind of stuff. Now, some people go totally crazy with this. A big UK charity called Comic Relief usually has one big auction per year. Now, that big auction per year is massively, massively spiky. If you don't have enough capacity for those 2 hours, you're losing money. If you have enough capacity for the rest of the year, you really don't care. Things fall over all the time. They're in panic mode before that. And they did this talk. You can watch this video. My slides are online now, so you can just download this and find this URL. So their campaign management, their kind of processing payments and things like that went down from $83,000 for that kind of 2 hours to about $5,000. That's 94% saving. Just because they don't have to worry about planning for capacity and predicting how much they need. They don't have to figure out in what parts they need this. Amazon or Google takes care of that, or Microsoft. So that's kind of the interesting thing about this. Now, when we look at how to get here, you can't just take an app that you've designed to work with containers or servers and take it there. There are libraries for that, but you're not going to get anywhere close to these numbers. In order to actually get this benefit, we need to start thinking completely differently about modeling and design. And that's kind of what I really want to talk about today. So one of the things that kind of is starting to happen in this world, because we are no longer paying for you're no longer paying for reserved capacity, there is no benefit to think about big applications anymore. There is no benefit to think about, oh, I'm going to kind of put these 3 services together and this thing, and there's this unbundling happening from applications to tasks. And then each of these tasks can scale independently. When you bundle something in a big app and then you say, okay, we need more capacity, then you get more capacity for everything. You don't really know whether you need the same amount of capacity for invoicing as you need for payment processing. Like, maybe they're 2 completely different things, but the way we were deploying stuff was rewarding bundling it together, so it all had to scale together. With deep coupling into tasks, then the cloud provider can kind of figure out, oh, for this payment processing thing, you need actually more capacity now. I will give you more capacity. For the other stuff, you're really not using it now, so don't worry about that. And that's why I think, when you look at what's actually used in an app at any certain point, who knows? I mean, it's very, very difficult to know with bundled apps. Because Amazon or Google or Microsoft are charging you per request, that's really interesting. They need to track what requests are going on, how much they cost. So you get like micro-level cost of the flows through your application if you decouple it properly. If it's all bundled, then you just get a single price. When you get micro-level costing, you can make better decisions around, well, this thing is costing us a lot. Is it actually that valuable? Should we offer a simpler version of it? Should we stop offering it, or should we invest in it? Or this thing is costing us quite a lot. It's making a lot of money for us. Hey, excellent. So this is kind of where I think part of the design change is designing more around tasks than designing around apps. And another part of that becomes really, really interesting is rather than thinking about one single core domain, that's kind of, this wonderful thing that we're going to build and protect and design and things like that, we actually start thinking lots more about, well, what is the core piece of this task that we want to do? In user registration, what is different for my app from all the other apps? What is the teeny tiny business kernel of that? And then we no longer have to think about, well, is user registration really core for us? That's, how do I decide? I don't know. Like, Nick talked about this morning, well, maybe this is core, maybe that is core. Maybe search, if you talk about it, search is really not core for us, but maybe there's a teeny, teeny, tiny piece of it that actually is. Thinking about big cores doesn't allow us to do that. Thinking about small tasks and small kernels of these tasks allows us to kind of start thinking about that in a much, much better way. So rather than thinking about core supporting generic and things like that for kind of the whole thing, we can start thinking about core supporting generic for teeny tiny workflows and thinking about them and optimizing them and designing them. So kind of the good news about this is because it's so, if you decouple an app to lots of small tasks, pretty much you get isolation out of the box. You get blast doors or fire doors everywhere. You get mistakes that are very, very easy to fix because they don't propagate. And the whole approach is very, very tolerant to making a stupid design mistake. Because, hey, we've made a stupid mistake in this service, we'll just kind of rewrite that and everything else will continue working as it is. And we very often look at things, the product I'm building, there's only 2 of us building it. We do everything from sales and marketing to support. So about a month ago, we were looking at some piece of code we wrote 3 years ago. So 200 lines of code. Like, we wrote it together, pair programming. Neither of us could understand how it works. Just staring at it and scratching our heads like. So instead of spending hours to figure out how it works and then doing characterization tests, doing lots of stuff, we just threw it away and wrote a new one. We kept the knowledge, we threw away the code. We fixed the design mistake. So the whole approach is very, very forgiving to design mistakes. That's the good news about this. And if you start thinking about decoupling from apps to tasks, the only reason why we didn't do that before is it was too expensive to operate. Thinking about how I'm going to operate every single task of my app on a separate infrastructure was like insanely expensive. Now it costs exactly the same as operating it on a single infrastructure. So the benefit is no longer there. So I think with traditional domain-driven design, people spend a lot of time thinking about where are my bounded contexts. Are my bounded contexts around teams? Are my bounded contexts around products? Should this be inside this context or outside this context? With debundling this stuff to tasks and decoupling it to tasks, well, hey, each task is potentially context. Like, who cares? I mean, if we made a mistake, we'll just fix it. It's not a big problem at all. Making a mistake about kind of contexts in a single app is hugely expensive. Making a mistake about context boundaries in a decoupled app is no problem at all. And I think that's why this is so powerful and empowering for people who design. Because yes, you can be a sloppy designer like me and still make a successful product that makes a lot of money, but it doesn't have to cost a lot in maintenance. So another thing that's kind of really interesting here is with traditional design around applications, we tend to look at conceptual consistency as the primary motivator for boundaries. Like, a payment means something in this, its words, its names, its structure. A payment means something completely different here. We're going to put an anti-corruption layer. We're going to kind of make it complicated. We're going to translate. But kind of a lot more I find myself doing boundaries around, well, this thing needs security access to this database. Therefore, when it loads a user, the user has this meaning. This thing doesn't ever access the database. When it gets a user, really, like, that can mean a completely different thing. I'm not saying you should do that every time, but there's an option of kind of structuring boundaries around security and access, and I'll talk about this later. And kind of the most important thing here is when you decouple this, because the deployment is decoupled, the blast radius for changes is relatively small. The blast radius for mistakes is relatively small because they're all decoupled into different tasks. So that's the good news. The bad news is that basically even Hello World is a highly distributed app. And you need to know how to design highly distributed apps from the start. And I'm really talking about design here, not modeling. But designing highly distributed apps is something that not a lot of people have experience with, because you don't need a high throughput transaction processing system usually for most of kind of the work you need to do. So this is where the problem becomes we cannot really ignore distribution. Traditional modeling and design imply distribution. Once you do design, the distribution is implied. With designing for serverless, if you really want to get the benefit out of this, you need to consider distribution all the way through. You cannot ignore it anymore. Now, kind of one of the, I said serverless deployments are very, very, very tolerant towards mistakes in design. There is one particular mistake that it's not tolerant for, and that's Martin Fowler's first law of distributed computing. Now, in, I don't know, 1995 or something like that, Martin Fowler published a book called The Patterns of Enterprise Architecture. And in Patterns of Enterprise Architecture, he defined the first law of distributed computing. And lots of people misquote that law and misremember it online, because you can find 1 million blog posts that talk about how Martin Fowler's first law of distributed computing is this. Just basically, if you are deployed on a distributed platform, you cannot really obey that. Now, Martin didn't say that. What Martin said is don't distribute your objects. That's the full first law. but that tends to be too complicated to remember. And yeah, even understanding objects, and that's a really good point. That's what I wanted to talk about. So, what do we mean by object? What Martin meant is, don't distribute in the domain-driven design sense, don't have a single aggregate on multiple machines at the same time, because you cannot guarantee consistency. It's going to be really difficult to work with it. So domain-driven design has, a bit more to say about this, of course. But so one of the things that becomes really, really important is how do we design stuff to obey this, but how do we actually not make the system a distributed monolith where everything is tied to everything else because we're not distributing objects. And that's one of the biggest challenges we're going to have. So with serverless, basically time is money. You pay for utilization. So if your application, when it loads up, needs to talk to 3 databases and needs to save something to 4 databases, that task is going to cost a lot. If the task doesn't need to do that, then it's going to be much, much cheaper. And that's how people save money, by considering deployment. So as a really stupid example of this, say you have a user uploading a file, and the user has some limitations, what they're allowed to upload and what they're allowed to do in the system, and they have an intent to do something with the file. They want to convert it, they want to save it, they want to send it, So not a good or bad, but let's say a way of designing this would be to create an aggregate around the user, the intent, and the limits. That's where the boundaries of consistency are. And then there's this file upload that has a reference to the intent. Now, in a database, that would be a foreign key. In a Java program, that would be an in-memory reference or something like that. But the designing something like this and then unbundling it into multiple tasks becomes interesting. What does a task that does this process, this file upload, need to do? Well, that one will need access to the user database to figure out who the user is. That one will need access to the intent system. That's probably some file system or queuing system somewhere. It will need to connect to 10 different things. This is an excellent way of paying Amazon more money. So if we look at minimizing the chattiness, because chattiness costs a lot, then we're going to say, well, yes, this is a nice little aggregate on paper, but what I actually hear is just give me the shit. Give me the file ID, give me the intent type, give me the user directory where the files are. I'm going to break this aggregate completely. And this is the problem this is the fundamental problem that we will have designing for serverless apps. This thing saves a lot of money, but is it dirty? Is it clean? I don't know. What? And conceptually, what is good design? Is good design something that saves money now? Is good design something where you can change it to some potential future later? And how do we balance these two things? So I think one of the critical challenges here is figuring out what do we even design. And I mentioned in a if you think about applications, you ignore deployment. Usually we model, and then from the model we infer a design. Of course, there's that happens at the same time, but deployment is an afterthought. Deployment is something that happens after you have a design. If we really want to benefit from this, we need to know this is going to be deployed separately like this, so I can design an aggregate around this stuff. We need to understand the deployment as well. So I think in the serverless world, the intended deployment has to influence the model. And that becomes a challenge, and the model influences deployment, and the design comes after that. The design is co-influenced by this. Another thing that is really a big difference is with the traditional design, because we don't consider deployment, we don't consider the element of time, as in time in memory, time in processor. That's ignored. You design a service. Will this service be transient, start, run? I don't know. With this, we tend to design much, much more shorter-lived tasks. And maybe that's one way of reconciling this, because the problem with breaking aggregates and consistency and things like that is the danger it happens when people start modifying stuff. If I design a smaller task that I know is not modifying this, and it only lives for 200 milliseconds, and we're not going to keep it around for long, then a lot of these constraints are no longer necessary to put there. And one of the things that is really, really interesting is in traditional application-based design, data transfer is a complete afterthought. Data transfer is something you use a generic library to serialize it into JSON or serialize it into XML if you're really crazy, Or, if you're so inclined, serialize some kind of binary protocol like Google protobuffers, that's completely synthetic. We design our objects, and then we're going to serialize this, or God forbid use an ORM or something like that. Please don't, but it's kind of an afterthought of that, where with serverless design, data transfer is actually the thing we need to focus on. It's kind of figuring out what bits need to travel through the network so that individual tasks have enough information without chatting too much to other tasks. And that's really kind of completely different from how we're thinking about design. Now, in this case, what I think is going to happen as we evolve practices around this is events will become kind of mini aggregates. And mini aggregates in a sense that they're aggregates for a specific purpose. They're aggregates for a specific task or a specific group of tasks. They're not aggregates in a kind of deployment kind of ignorant way. And one of the other things that kind of really becomes interesting here is when we think about design of applications, we usually talk about, well, focus on the core and design the core well. All the ugliness just pushed to the boundaries. We'll do an anti-corruption layer. Like, we'll unit test it, we'll translate there. Don't worry about that. And Nick was talking about this morning how, people are obsessed with boundaries. I don't think so. I think people ignore boundaries when they design. And I think kind of the problem here is with kind of serverless being tolerant to design mistakes apart from the protocol, really the boundaries are the things we need to be designing. And everything else is fixable later. If your service has a good protocol in and out, you've made a huge design mistake in it, it works bad, it's okay, just you replace it, the protocol is the same, no worries. If you've not designed the protocol well, nothing is going to save you. So I think it's kind of, this is a bit turning the design on its head. We need to design different things. And again, this is coming from highly distributed systems. I remember talking about this with somebody who used to work for Ericsson for about 30, 40 years. And he said, well, Erlang systems 30 years ago, we had this rule, design the protocol, everything else doesn't matter. Well, yeah, that's kind of highly distributed system. That's why I think, people don't really think about this the right way. So there's two ways of designing protocols for network that I know about. There's kind of some other stuff that are derivatives of this. There's kind of remote procedure calls. Remote procedure calls are pretty much, we have a tight coupling between the caller and the callee. They share an interface. It's kind of usually a shared kernel or some library or something like that. And the remote procedure call tends to pretend that the network doesn't exist. Usually they're done by proxies, which is, you magically create proxies. These were web service proxies, or they were Java Bean proxies, or WSDL proxies, and it's every 5 or 10 years, somebody reinvents another technology that's magically going to solve all world's problems through this. And we have events or messaging. Events or messaging are kind of more open host. Events or messaging are saying, look, a user registered. Like, if anybody needs to do something about this, do it. I'm not going to imply, send an email or, confirm this, or, like, whatever you want to do it. So events or messaging they communicate maybe an intent of a user or a fact that happened. They don't tie with the interface on the other end. Now, the big difference between these two is about 2 years after people implement RPC, they kind of go and cry and suffer badly because the reality about network not existing when it actually exists hits them, and then everything falls apart. And we've learned that kind of event-based systems are a lot better. And of course, the stuff in between, you can send kind of commands and things like that. But the really interesting question becomes, how do we design, and I think this is kind of one of the core problems that we're going to have in the future, how do we design these events so that they're not coupled to the receiver interface, they're not coupled to the receiver implementation, like, hey, a user registered, but they still send enough information to these things so they can finish without chattiness. It's very easy to say, hell, a file upload happened with this file ID and an intent ID, but then who needs to work? Well, go and read 10 databases about this. But if we say, hey, this file ID happened with this intent and this limit, how are we not really implying an interface of what needs to read it? And balancing this stuff becomes really, really challenging. And that's why I think having these boundaries, having meaning and language and events around a single receiver is bad. because then we're tying ourselves too much to this. But maybe what's going to happen is kind of, we need to start thinking about decoupling these things into groups of services. So the traditional application-based design would say, okay, we have this kind of payment service, we're gonna, it's payment, so it's important, so we're gonna put our best security people on it, they're gonna design it like crazy, it's going to be secured, it's going to be scalable, it's going to be wonderful, it's going to kind of, use queues to asynchronize things and then talk to payment providers. And one of the things becomes kind of, how do we decouple this into tasks, and how do we decouple this into, where is the right context for this? So we had a relatively interesting design discussion, thinking about deployments when we were thinking about this. And one of the things that you usually have to use for every single payment provider is you have to use their own library for this. Now, when you have to use their own library, it comes with 5 million dependencies, because you do Maven install, it downloads the whole internet, you do NPM install, it downloads the whole internet. And we kind of had a problem where one of the payment providers we were using had a security vulnerability in their dependencies, but so there's a trade-off. Like, do we want to use that payment channel? We're getting a lot of money from it. From a business perspective, yes, we want. From a security perspective, they have a vulnerable dependency there, which is deployed in my payment service. So all my securing stuff around it doesn't really matter. We know it has holes in it. And because it's a single payment service, it has full access to this database. So from a security perspective, no. And what we started realizing is kind of maybe thinking about these boundaries around security needs is interesting. Like, what does this task actually need access to? This task that has access to their library, well, it needs to kind of talk to the network, and it needs to talk to this thing here. It doesn't need to talk to my database. If I start thinking about tasks, not services or applications, I can start thinking about, well, I'm going to have a function or a task that talks to this payment provider. We're going to put their library in it. It has access to the network. It doesn't have access to anything else. It can post a message onto the queue, and that's fine. And this is where kind of things became really interesting, because what we realized is kind of, there is a context around this more generic stuff that we have. And in that context, we used our models, we used our language. We pulled out everything that has dependencies on third-party libraries outside the payment service, and then allowed every single provider to use its own language. We had a stupid amount of complexity when everything was together on Heroku, because in the same memory process, we had to translate from all of these different concepts that people have and figure out what it needs to do. And now we can actually have, well, in this context here, it uses the PayPal language. In this context here, it uses the Stripe language. In this context here, well, it uses our stuff. And of course, this is kind of a, with hindsight, this is a good solution. But what I'm trying to say is, when we started considering security needs, we started seeing boundaries that we didn't see before. And this allowed us to kind of think about, well, what third-party library do we want to load here? Does that actually require a different context, different language? Does it need access to the database? If it needs access to the database, maybe it's inside this context, maybe it's not. And we started thinking about it. So I think kind of one of the really interesting things is kind of we started grouping tasks as bounded contexts around runtime security needs. And that's why, again, why I think ignoring deployment, where runtime security needs come in play, while we're designing is kind of a wrong thing to do. So another thing that is interesting kind of to think about, and I'll finish on this, is when we look at infrastructure. The infrastructure really, when we are designing applications, it tends to be stateful or stateless. We know that this service is stateless, we don't care. This service has a cache, we care, and things like that, where because a provider controls the infrastructure, the provider basically can just throw away your services at any given point. They can drain them, they can send stuff to you, they can spin them up. And a lovely thing about that is you get a lot for free. For example, in 2018, there was this problem with Intel processors, and everybody went crazy about that, and a month later there was another security issue there that was kind of less publicized, but we got an email. I woke up 8 o'clock in the morning, I got an email from a school administrator in the US saying that, this vulnerability in Intel processors has been discovered. They want all their vendors to kind of immediately say what they're doing about this. I'm still waking up, my head's not in the right place. I'm drinking coffee, so I copied the CV identifier, I put it into Google to find what it is. the first result on Google said Amazon Lambda has already been patched. And that's why, this is amazing. You kind of, security is a wonderful thing, but it's not my core domain. I've hired that from Amazon. And because they own the infrastructure, they could just kind of drain stuff, replace it, and nobody's kind of, interested about anything. So, we're moving away from this idea of reserved capacity to utilized capacity. And not even that, but we're getting crazy functionality now. Like you can do a gradual deployment. This comes out of the box. You can do, while you're deploying stuff, you can say, well, give 10% of the requests, send 10% of the requests to the new version of my app, send 90% of the requests to the old version of my app, or kind of gradually move that thing around, monitor for something weird happening. If something weird happens, send everybody back to the old version of the app, kill the new version, or if nothing weird happens, just keep giving it users. 5 years ago, you could only do this if you were Amazon or Google or Microsoft, or Facebook maybe. Doing this would cost twice as much as operating your production. Doing this now doesn't cost anything more than operating a single version because it's priced based on the number of requests. And stuff like this becomes amazing because you can also, in a weird inception way, define a Lambda function that tells this thing what something weird is. So you can monitor, for example, sales conversions on the new and the old version. That's your unique thing. Deployment and exceptions are not your unique thing. Your unique thing is how you track sales. Deploy that, then, send a new version, and if for some weird reason, the new version of the app is making people buy less, well, there is a bug. It might not be a bug that was caught by unit test, integration test. There is a bug. It's, something's weird. Roll back. And again, that's allowing us to do kind of interesting things about this. So kind of, to conclude, with serverless, there's a ton of benefits from considering deployment when we're designing. And usual application-based designs, they tend to model and design thinking that kind of, okay, we know that this model is going to evolve over time, but at any given point, the model will be consistent. Like, at this particular point, the model for a user in my application is this. But if I do this, well, I might have two versions of my application running at the same time. What is the model for a user? Like, what do we do if this first task, the save stuff to the database, has a new version that saves a different model to the same database? And the previous one can, load that during this transition. And I think this is where kind of we need to start assuming that model no longer just evolves over time, but kind of evolves over space as well. And that at the same time, in a deployment, we might have an inconsistency between the models. And what I think this is going to lead to is kind of it's going to lead us to think about, well, model not as a universe, but this comic multiverse stuff where everything is connected to everything else, and it's weirdly similar but different in some ways. But if we can achieve that, the benefits are amazing. What we can do if we can design an app for this is, yes, we can do gradual deployments, but we can also do stuff like, we have a really important customer, they have a specific need, we can implement the need for them in 1 week, but in order to make that consistent for all our other customers, we need about 3 more months. Usually what would happen is you finish that, then you make it consistent for 3 more months, then you give it to your customers. This way, hey, we finished enough for this customer, completely deploy a new production version of the app for this customer, give it to them, let them use it, let them benefit, then clean this other stuff up and then move people gradually over to the old version. It costs exactly the same as the other approach, just 3 months faster, because it's priced based on utilization, not priced based on environments. So kind of what I think we'll need to start doing is think about version-tolerant design. Think, how does something upgrade and downgrade and regrade and who knows what else with the aggregates that are coming in. And we started putting version numbers on everything we send out. That allows us to say, okay, now we're replacing the service, and we recently had to replace the Stripe integration. No problem at all. We say, okay, we are keep pumping messages version 1 into the queue. The old one is picking them up. We pump 5% messages version 2 into the queue, have both versions running at the same time, see what's happening. And kind of stuff like that is really, really interesting to consider, because I don't think we think about versions in our model enough when we design. So that's pretty much it for me for today. I hope I've kind of tickled your imagination at least a bit. I wrote a book about serverless deployments and design. It's called Running Serverless, and as a small present for suffering with me through our, you can get like 50% off if you go to this URL this week. Thank you very much.